So in this short video, I'm going to go through the t-test, when we do it, and how we can apply it to an exam question. So the t-test is used when you want to compare means. So if you go out and you do data in one place and you collect data in another place and you want to see if the means are significantly different to each other. So for example, imagine you've measured the length of leaves found in 2 different areas. You've collected 8 leaves in each, and you've calculated a mean and plotted a bar chart. So 2 different areas, you want to see where there's a difference in the length of the leaves. So this is the graph that you might get. So you can see straight away that A seems to have a mean of approximately 22.5 centimeters, and B has a mean of 31. So looking at it, we would say, and quite reasonably, that yes, B has longer leaves than A. However, the question is, are they significantly longer? Is it scientific reason or is it due to chance? And how can we tell? We can tell by using a t-test. Now, this becomes important in evaluate questions, because in evaluate questions, you might look at this and go, yes, B is longer than A. But now we actually want to see whether statistically there is a significant difference between the two. An example of where this might be used in real life is in something like drugs trials, where they're producing a second drug and they want to see if it's a significant improvement on the first drug. Is it worth spending all the money in production? So in order to look at whether it's significantly different, we do a t-test. Now the t-test is used to tell us the probability that the difference in length is due to chance. Now, obviously, the smaller the probability that it's due to chance, the better, because it means that it's more likely that it's due to a scientific reason. So first of all, you create a null hypothesis. A null hypothesis says that there is no significant difference in leaf length in the 2 areas. So null is always no. So if I go back to my drugs example, there is no significant difference between drug 1 and drug 2. Always about the idea of no. You're testing a null hypothesis to see whether you accept it or reject it. So first of all, you calculate your t-value. Now, you will not be required to calculate a t-value in AQA A-level biology within the exam. If they want you to use a t-value, they will give it to you and ask you to compare it and actually evaluate the value. You may be asked to calculate degrees of freedom. Degrees of freedom are calculated by the number of samples that you're taking minus 2. So in this particular case, we had 8 in A, 8 in B, which gave us a total of 16. Take away 2, we have 14 degrees of freedom. Now, what do you do with that? Well, the answer is you have to look at it and compare it to what we call a critical value from the table. So here is a critical value table. Here is 14 degrees of freedom. And our critical value is 2.15. Now we'll look at what that means in a minute. But the other thing I want to focus on is this value over here. This is a probability value, and it's a probability value of 5%. So this is going to tell us whether there is more than 5% probability that the difference is due to chance, or less than 5% probability that the difference is due to chance. So that's what we're going on to see. How can we use this critical value table to determine whether it's more or less than 5% probability? So let's come back to our critical value table, which is over here. And we're going to say, let's imagine my t-value, my calculated value is 3.05. So what does the critical value tell you? Well, the critical value tells you the minimum value you need to say there's less than 5% probability that the difference is due to chance. Or if you think about it the other way, although we tend to write it like that, there is more than 95% probability that the difference is due to a scientific reason. So we've got a reasoning behind that. So we look at my value. So my value is 3.05. And I think, well, if my value 3.05 is greater than the critical value, that means there is less than 5% probability that the difference is due to chance. In other words, my difference is significant and I can reject my null hypothesis. So once again, let's look at it again. This was the minimum value you had to get to say that the difference basically wasn't due to chance. I got a value bigger than that, so I can say straightforward that the difference is significant, and I can reject my null hypothesis, and there is less than 5% probability that the difference is due to chance. In other words, I'm more than 95% sure that the difference in the results is something due to science. It's really important that you learn to interpret these values. Now, you'll notice I use the word difference, and that is crucial. You are not looking at whether the results are significant. You are looking at whether the difference in the results is significant. In other words, is B significantly longer than A? Well, in this case, yes. There is a significant difference in the length between B and A, and that's that B is significantly longer. And there is less than 5% probability that this difference is due to chance. Now, in an exam, they often don't give you the t-values. Instead, they make life easier. And instead, they give you this value over here, which says that the probability is less than 0.05. So if you look at that, that means there is less than 5% probability. Okay, so that comes from the inequality. So if you've got a less than, you can take that as the probability is less than 5%. We'll write it the other way. There is less than 5% probability that the difference is due to chance. Okay, so they often say that in an exam. So it means exactly the same as we said before. If the probability is less than 0.01, then there is less than 1% probability that the difference is due to chance. In other words, it's even more significant that the difference than it was before. If, however, they tell you that P is bigger than 0.05, or your t-value that you calculate is smaller than the critical value, then the opposite is true. The difference is not significant, and there is more than 5% probability that the difference is due to chance. Now, let's have a look at an example of where this would be applied in an exam question. So, in an investigation, the population density of plants in a regularly cut lawn was compared with that in a lawn which was only cut occasionally. The table shows the results, and we have a mean population density, which means we are doing a t-test, because that's what we do when we compare means. So we're looking at daisies. What is the population density, the mean, when a regularly cut lawn is 36? In an occasionally cut lawn is 18.6. So again, straight away you can see that 36 is bigger than 18.6, but to know whether it's significantly bigger, we have to look at the results of the t-test. So my advice is, if you're given a table like this, is to go down and think. You need to think, is the probability less than 0.05? Because if it is, then the difference is significant. On the other hand, if P is greater than 0.05, the difference is not significant. So straight away, just go down and look at those values. And my advice is to write next to it, not or is. So this one probability is less than 0.02. So it is significant, we'll just write sig. This one is less than 0.05, so therefore it's significant as well. This one is less than 0.01, therefore it's also significant. These two are not significant because the value is bigger than 0.5. Okay, which is obviously bigger than 0.05. So we now know that the daisies, the dandelions, and the field buttercups have a significant difference in mean populations. So daisies have a significantly higher mean population on the regularly cut lawn. Dandelions have a significantly higher mean population on the regularly cut lawn, and field buttercups have a significantly higher mean population on the occasionally cut lawns. However, the plantains, there is no significant difference between them. Now, just one more thing to bear in mind as we're looking at these results is you'll notice that this is 0.05, this is 0.01, and this is 0.02, which tells us that out of all of those three, field buttercups is the most significant, because that, if we were to look at percentages, that is less than 1% probability, that is less than 5% probability, and that is less than 2% probability. So we can say quite easily that the field buttercup has the most significant difference in mean population density. But when answering this exam question, I would then go on to be really clear. So I would say daisy, dandelion, and field buttercup have a less than 5% probability that the difference is significant. And field buttercup is the most significant because it's got less than 1% probability. Ribwort plantain and greater plantain have a more than 5% probability that the difference is due to chance, and therefore it is not considered as significant. Okay, I'll say that again. Daisy, dandelion, and field buttercup have a less than 5% probability that the difference is due to chance. I.e., it is significant, with the field buttercup being the most significant. Ribwort plantain and greater plantain have a more than 5% probability that the difference is due to chance. I.e., it's not significant. Okay, so there's no significant difference there. So the minute you're given probabilities, start thinking what they mean.